the chain rule, since we know how to take partial derivatives. So there is, we're going to review what happened in the single variable case, and then we'll see, as we saw at the end of last lecture, there are a couple of cases where you can, there are two different chain rules now in multivariable. So the good old chain rule, remember that I have a function f, and then I'm going to evaluate, I'm going to substitute x by some other function g of t. So what I end up getting, the composition of the two is f of g of t. And then I can, now that function, that composition is a function just of t, so I can take a derivative. And that derivative is going to be the derivative of f as if it was just with respect to x, but evaluated still at g of t times the derivative of g with respect to t. That's what happens in the chain rule. So if you just use the prime notation, the derivative of f of g of t of a composition is the derivative of f evaluated at the inside again times the derivative of the inside. Okay? So just as an example of how that works, I'm just going to write it in here again, that the derivative of f of g of t is the derivative of f evaluated at g of t times the derivative of g. So in this case, if I want to take the derivative of this composition, I can simply take the derivative of f, which is cosine, but evaluated at what g was, at t squared plus 1, times the derivative of g of t, which is 2t. Okay, so it will be 2t times the cosine of t squared plus 1. Okay, that's my derivative. But now in multivariable calculus, now the situation is that I have a function of two variables, and the first situation is where I am going to substitute the x for a function of t and y for a function of t, so that the result, now what I would like to know is what happens with the derivative of f of g of t, h of t. I'm trying to compute, this is a function of t, so I'm trying to take a derivative with respect to t. But my original function f has two variables, x and y, so what happens, the answer is that the derivative is going to be the derivative of f with respect to x evaluated at g times the derivative of g with respect to t plus the derivative of f with respect to y evaluated at, again, at this gh, and then times the derivative of y with respect to t. Okay? So let's see what happens. So let me expand this formula again. The derivative is going to be the derivative of f with respect to x evaluated at those functions g and h times the derivative of the x, which is the new values at g, so is the derivative of g with respect to t, plus the derivative of f with respect to y, that is a function of x and y, so I have to evaluate it at the functions g and h times the derivative of this function h with respect to t. This is what, sort of like the generalization of what was happening in the single variable. So let's see an example of how that works. So here are my function f, my function g, and my function h. So first, let's figure out the partial derivatives of f. So the derivative of f with respect to x is, well, what is it? 2x. The derivative of f with respect to y is just 1. I'm going to need the derivative of g with respect to t, and that's going to be a power rule, 4 times 3, so let me just make it a 12. 12 times t to the 3 plus 0, and the derivative with respect to t of h is just 3. Okay? So I have the formula down there, so now I can compute the derivative with respect to t of the composition of f with g and h is going to be the derivative of f evaluated at g and t. Okay, so my new x, this is what x is now, and this is what y is now. So I have to take the derivative, 2, and evaluate it at the inside, so at g and t. In this case, x is g, so times 3t to the 4 plus 1 times the derivative of g with respect to t. So times 12 times t cubed plus. And then the second term is the derivative of f with respect to y, which is 1 evaluated at g and h, but 1 evaluated at g and h for x and y is just 1, times the derivative of h with respect to t, which I calculated it to be 3. So all in all, I get something like 24 t cubed times 3t to the 4 plus 1 plus 3. Does that make sense? It doesn't make a lot of sense to me. I sort of like know where this formula comes from, but right now for you it's just a formula. But we have another way of doing this using the single variable chain rule. So let's see that it actually works and that I get the same answer. So using the single variable chain rule, this one, the other ones that we're not going to be able to use this, but in this case I can actually just do it the old way, because how much is f of g comma h? I can evaluate, and this is 3t to the 4 plus 1 squared plus 3t, right? And now this function is just a function of t, so I can take the derivative with respect to t of this, and what is it going to be? Well, it has to be the derivative of x squared, which is 2x, evaluated at the inside, so 2 times 3t to the 4 plus 1 to the 1, times the derivative of the inside, which is 4 times 3 times t cubed. So it's 12 times t cubed, plus the derivative of 3t, which is just 3. So this is, like before, 24t cubed, 3t to the 4 plus 1 plus 3. So at least in this case, we see that the new formula agrees with the old formula. When you substitute, it's all one function of t, and then you can just use the old chain rule. Yes, but sometimes we're not going to know what the expression is for f. We're just going to know some derivatives. So this is the derivative function at all points. But sometimes you have some data for the derivatives at one point, the partial derivatives at one point for a graph. And then you want to know what is the actual derivative if I go in this direction of t. So you don't have all the information to plug everything in. So that's why we developed this formula that works as treating it as a two-variable function. So now the second case is the more complicated one for the chain rule here in two variables, is that I have a function in two variables, and I could substitute x and y in terms of functions in terms of two other variables. So we have x and y here, and now x is going to depend on s and t, and h or y is going to depend also on s and t, and I'm going to plug everything in. So the result is that I get a function now. When I plug everything in, I'm going to get a function f of g of s and t, comma h of s and t. So you see that this is going to be some function of s and t. So I can take derivatives with respect to s. I can take a derivative with respect to t. And each one has a different formula, which is similar to the first case, as if you treat this as t is just a constant, and I take a derivative as if s is the variable, or treat s as a constant, and then take the derivative as if t was the only one variable. Okay, so let's see how that works in an example. So here is one of those. All right, so let's start. Let's do things a little bit systematically. So let's find the derivatives of f first. The derivative of f with respect to x, it's just x squared times a constant, because now y is a constant for me. So this is 2x times that constant. So this is 2x y cubed. The derivative of f with respect to y will be 3x squared y squared. And now I'm going to need the derivatives of g with respect to s and with respect to t. So let's start with the derivative of g with respect to s and the derivative of g with respect to t. G with respect to s, this is just s times a constant, so it's a constant, so it's cosine of t. G with respect to t is, well, the derivative of cosine of t is minus sine of t, so I get minus s times sine of t. And then I'm going to need the derivatives of h with respect to s and of h with respect to t. H with respect to s is just e to the 2t, while h with respect to t, that I need a chain rule, that is 2s times e to the 2t. Okay, so now I can compute the partial of the function now. Let me write the function. So z was, this whole thing here is my new function. So let's write like in the formula, the derivative with respect to s is going to be the derivative with respect to x evaluated at g and h. Okay, so this is a lot, but it is what it is. 2 times x by evaluated at g, it gives me s times cosine of t, times I'm evaluating in here with g and h. Okay, so instead of x, I wrote this one, and h, which is s times e to the 2t cubed. That is just the derivative evaluated at g and h. And then there's one more term. I have to multiply by the derivative of x with respect to s. So the derivative of g with respect to s. So I have to multiply also by cosine of t. That is this term. This term. So this whole thing is this term over here. Okay? And then I'm going to add the second term. The derivative of f with respect to y is this, but I have to evaluate it at g and h. So I get 3 times s cosine of t squared times s times e to the 2t squared. And now multiply by the derivative of y with respect to s. So the derivative of this h with respect to s, which is another e to the 2t. So this term here is corresponding to this term here. Let me maybe do it in a different color. This term here corresponds to this term here. Okay? And that's the answer for one of the derivatives. That's the derivative with respect to s. I'm not going to do the derivative with respect to t, but it's just similar to all of this. Okay? Any questions on this? So I'm going to leave the derivative with respect to t. That would be this formula here that would go into this whole thing. This part. So in this part, I'm following this recipe here. So it's, first of all, the derivative of the function with respect to y evaluated at the inside, at the old inside. So I evaluated at g and h. So I have to evaluate this at g and h. So it's 3. X is s cosine t squared. And then that y is h. So s e to the 2t squared. So that part is the derivative of z with respect to y evaluated at g and h times the derivative of y. The y corresponds to the new y is this formula for h. So the derivative of h with respect to s. So that's why I did it here, is e to the 2t. So that's the extra factor that corresponds to the g prime of t at the end of the old chain rule. This cosine t is the derivative, this corresponds to this, is the derivative of x. My new x is here. Okay, my new x is here. So it's the derivative, is this derivative of x with respect to s, which is in here. The derivative of g with respect to s. When I take the derivative of this as a function of s, this is a constant times s. So the derivative is just the constant, which is cosine t. So this is the chain rule in the second case.